my lecture today. Of course, today we actually starting chapter 10, and that's going to be the last chapter of the semester that we call the 1-2 sample hypothesis testing of proportion. That is what we're going to walk through today. Let me just tell you, generally speaking, statistical inference is about two things. Okay, when I talk about statistical inference is about two things. Number one, estimation. Number two, hypothesis testing. Okay, statistical inference is about two things: estimating parameters, and at the same time we test hypothesis. Now, what we've done before now, I've walked you through how to estimate. Okay, when we talk about estimation, we got two types of estimation: point and interval, right? I've walked you through interval estimation. I remember I walked you through interval estimation for single mean for one population, mean for two population. We've also worked on constructing confidence interval for proportion for one population. We do the same for two population. So we've actually work on constructing interval. Okay, when you have, why do I need to construct an interval? Why do I need to do interval estimation? Of course, I need to do interval estimation because a single value could be wrong or right. When you have a point estimate, the point estimate is a single value. It could be wrong or right. We don't want to waste resources. We don't want to waste time. Imagine you commit a lot of resources to your findings, and in the end, only to be let down by, poor statistical tool. And the only way we can rely on our estimate is to construct an interval. I've already walked you through that. But what is new? What is new is we may want to test hypothesis about a particular value of a parameter. Our mind can never be empty. Maybe there's a claim, and you know what? Investigation follows every claim. If somebody make a claim, there's going to be investigation. What are we doing in investigation? We are testing the validity of a claim. So that's what I'm going to be walking you through. But in the outline for today, I'm going to first walk you through the method of maximum likelihood. Why do I need the method of maximum likelihood? There's no way I'm going to conduct an hypothesis without first have a way to estimate my parameter. Have you ever wondered, like, how do we know that this is the formula? How do we know if I want to find mean? How do we know that this is the formula we're going to use? How do we know if I want to find, for instance, if I want to find the population variance, how do I know this is the formula that I'm actually going to use? And how do I know if I want to deal with the sample? How do I actually know that this is the formula that I actually going to use? Where do they come from? I'm going to show you in the method of maximum likelihood where they come from, the distribution, the probability distribution that was assumed before we derived them. Then we're going to talk about that. And I'm going to introduce you to hypothesis testing. Then I'm going to walk you through some element of hypothesis testing. Then today we're going to focus on hypothesis testing that has to do with proportion for one population and for two populations. Let's get started. Let's get to business. Let's look at the method of maximum likelihood. Let me tell you this. We got method of estimating parameter from a probability distribution. I remember before now, you've done probability distributions, normal, exponential, gamma, and so on like that. Do you know that before I can actually compute important statistics from data, I need to know the probability distribution of the data set. I'm going to say that again. Before I can actually compute any meaningful statistics from data, we need to be able to understand its probability distribution. If the probability distribution is normal, of course, I know there are two parameters in a normal distribution, mu and sigma. Then I need to be able to know how am I going to get the mu? How am I going to get the sigma? Then we are actually going to use a method of maximum likelihood to be able to estimate the parameters of a given probability distribution. I'm going to say this again. When you have a given probability distribution, it could be normal, it could be exponential, it could be gamma, it could be Weibull, it could be whatever. Every probability distribution has parameters. You know that? Every probability distribution has parameters. How do we estimate them? If we want to estimate them using the method of maximum likelihood, then it means we actually need a likelihood function of that particular distribution. Then we're actually going to maximize that. And, if you want to maximize that, we're going to use the principle of optimization in mathematics to be able to do that. Now, what I'm trying to show you now, if I want to use the method of maximum likelihood, assuming a particular probability distribution, let us assume the probability distribution is just this guy, f of x theta. This f of x theta could be whatever distribution you've been taught in this course. Maybe my interest is getting the parameter theta. If f of x theta, okay, is for a particular distribution, and I want to use the method of maximum likelihood, I need the joint of this. What is the joint? What I'm going to do, I'm going to assume that this is just for xi. Then I'm actually I need x1, this one, theta, this one, theta, until I get to this. What am I talking about? Oh, I'm looking for information theta, and I go from one person to the other in the sample. This is the response of the first person. This is the response of the second person. But in each of that, I'm seeking for the same information. What is the information here? The information is actually theta that we also call parameter. Does that make sense to you now? I'm going to multiply them. Multiplying them, it means that's a likelihood function. What likelihood means is just multiply them. If I want to write this in short form, you know what I'm going to do? It's going to be I start from 1 to n, f of xi. This is a short way to write all this. That's exactly what I'm displaying on the board. What am I trying to do? I actually want to use the method of maximum likelihood, okay, to estimate the parameters in an assumed distribution. I want to give you an example of a distribution now that you've done in this course, Poisson. I need you to pay attention to this. You know why? the probability that a question from this area will be set in the final is 1. Please pay attention, but I want everyone to pass. Now, you have a Poisson distribution. Theta, this theta here in the Poisson distribution is mu. Mu. Poisson only has one parameter, mu. What am I going to do? Oh, I basically want to estimate that parameter mu, okay, by using the method of maximum likelihood. What am I going to do? I will actually, do this, take a look at what I have now. What I'm trying to say is my f of x mu is actually this mu raised to power x over x factorial s start from 0, 1, 2 to infinity. This is a Poisson distribution. I'm seeking to get the MLE, the maximum likelihood estimate of mu. I'm actually going to get the likelihood. Okay, the likelihood of this is going to be I start from 1 to that, e raised to power this, mu raised to power x over x factorial. You know what I'm going to do now? It's like I'm actually going to have this in a joint form, So when I have that in a joint form, it's like I'm actually going to have this guy in n term. When I have this guy, when I have u raised to power x1, u raised to power x2, until I get to u raised to power x. And what does that mean? I want to have this guy in an n time. I also want to have this guy in an n time. So this guy is just going to become exponential raised to power n mu, because in n time. And this one is going to be raised to power summation x. Why? If I take one mu, it's going to be this plus that plus that plus that, which is summation x. Any question? Okay. So this is going to be raised to power summation s. So that is why you have that. And x factorial in n, when you take a look at the joint, I'm still going to have this guy here. Do you know what I'm trying to tell you now? This is the likelihood function of a Poisson distribution anywhere in the world. Does that make sense now? Now, if I have this as a likelihood function of a Poisson distribution, what is the next thing I'm going to do? Take the log of the likelihood. Take the log. So taking the log, okay, when I say the log, I mean the logarithm of the likelihood is going to be log of L, the log of L, okay, is going to be log of, I'm going to have log of this guy, the log of this guy, right? Mu raised to power that divided by this guy. Take a look at that. So this is more or less like log A times B. So I'm actually going to have the log of that is going to be n mu. The log here is a natural log. Does that make sense? Natural log. Okay. Now here, this is going to be summation s log mu, right? Going to be a plus because of a product, then it's going to be a negative. Does that make sense? Minus log this. Any question on how I take the log of that? Any question? Any question? You're all good, right? Okay. Now, when I have, this is an expression for the log of likelihood. The next thing I'm going to do is to differentiate the log of likelihood with respect to mu. The knowledge of calculus is required here. Now, I want to differentiate. So when you differentiate that, let's say we're differentiating with respect to mu. Okay, differentiate this guy with respect to mu, right? Respect to mu, that is a minus n, right? Take a look at that. That was why you have minus n, right? Now, differentiate this guy with respect to mu. Of course, if from mathematics, from mathematical law, okay, from mathematical law, if y equal ln x, you know the y dx, the y ds is basically going to be 1 over x. This is from the calculus. Okay, so I now want to differentiate this guy with respect to mu. this is going to be 1 over mu, summation s 1 over mu, which is going to be summation x over mu. Okay, so if I do the mu log n is going to be minus n plus summation x over mu. This guy is going to be 0. There's no mu here, right? It's going to be 0, right? Then you set that to 0. That's an optimization. You remember in mathematics, when you differentiate, you set that to 0, you want to get a critical value, right? Now, when you set that to 0, what happen now? So setting this to 0, you're going to have summation x equal to n. Okay, what is your mu? Okay, so your mu here is going to be summation x over n. What is the mu? The mu is s bar, summation s over n. Any question? Any question? So I will advise that you know the likelihood function of a distribution. Now, I want to take you to the more important one. The method we'll be using, focus on normal distribution, right? When you have some data set, if you take a look at the confidence interval we did on mean, we are assuming that is from a normal distribution. Now, if I have, consider a random sample x1 up to xn from a normal distribution, with how many parameters do we have in a normal? We got 2, mu and sigma. Find the maximum likelihood estimators for mu and sigma squared. You know what you're going to do? You first start by writing the likelihood function. But if you want to start, that is not the way to start. You first write the distribution. Where I start here, I started from the likelihood function. But this is where to start from. I'm going to show you now where to start from. Give me 1 second. So where to start from? Okay, if x follow normal with this, okay, f of x is 1 over square root of 2 pi sigma squared exponential raised to power this x minus mu over sigma all squared. This is the distribution. Now, if I want to estimate the mu and sigma squared using the method of maximum likelihood, then I need to get the likelihood function for this. The likelihood function is more or less like, okay, my likelihood function subject to this is just going to be products, the joint. You know, you're not talking about product now, you're talking about the joint, right? You're talking about the joint, and we are using the idea of independence. You remember independence? When we talk about the joint, it's like you're trying to say the probability of the joint can be written as the product, right, of the marginal. So what I mean here now, it's like I'm trying to say 1 over 2 pi sigma squared, introducing a pi, okay, an exponential raised to power this x minus mu or sigma or squared. Now, you know the meaning of this pi? This pi is a product. It means everything here raised to power n. The constant here raised to power n. And here, for the exponential, this is going to have a summation. Because when I have exponential, if I have it in a multiple time where they are multiplying themselves, I'm only going to write one exponential and I'm going to add what is on the top. And that's exactly what you see here. Take a look at that. Is that not what you see for the first? Look at the first one. That is the likelihood of a normal distribution anywhere in the world. When I have the likelihood of a normal distribution, I can take the log of that. After taking the log of that, I got 2 parameters. I'm actually going to do partial derivative. And a situation where you got 2 parameters, more than 1 parameter, is going to be partial derivative. For us going to differentiate the log of the likelihood with respect to 1 parameter at a time, or treating the other parameter constant. For example, when I differentiate it with respect to mu to get that result, it means I've treated sigma as a constant. Then I'm also going to do the same, differentiating with respect to variance. Now I'm going to get that. And in the derivative with respect to mu I'm going to set that to 0. I will solve for mu. Okay, when I solve for mu, that will give me summation S over n. And that is the reason why in real life, if data set follow normal distribution, if you want to find the mean, you're going to use that formula. That formula of the mean actually comes from here. What about the variance? When I do the same thing to the variance, I'm actually going to get this. But you know what? This is the one for population variance. What we do in statistical analysis, we adjust that, creating the degree of freedom. Instead of using 1 over n, we're going to use 1 over n minus 1. Any question on that? Any question? Any question? What if I give you a distribution and I ask you to use the method of maximum likelihood to estimate the parameter in that distribution? All what you just need to do is get the likelihood function, step 1, take the log of the likelihood function, then differentiate with the differentiate the log of the likelihood function with the respect to the parameter, set it to 0, the resulting expression to 0, then solve for your parameter. That's how to do it. Any question? Any question? Okay. Now I want to introduce you to, before I introduce you to that, take a look at this example. Suppose 10 rats are used in a biomedical study where they are injected with cancer cells and they're given a cancer drug that is designed to increase their survival rates. This is research. You see that? They injected cancer cells and they were giving cancer drug, okay, to increase their survival rates. I think they are using rats here to do this because they actually realize physiologically, okay, the body of the rat and you know, human being function similar way. But when I talk about physiology, I'm talking about the functioning of the organs. When I talk about the anatomy, even though rats, the organ of the rat and the man are not the same. That's what to talk about anatomic consideration. But when you want to talk about physiological aspect, we talk about the functioning of the organs. Now, the survival time in months for those rats are this. But you know what we want to do now? The question now said that the exponential distribution applies. You remember? When we talk about survival rate, exponential distribution can actually be used because it's a probability distribution that we use to model the waiting time before the occurrence of an event. We're talking about survivor. How many, how many months these rats that they were actually subjected to this condition, treated, how many months are they going to live before the occurrence of death? Now, we now think of exponential distribution. I need you to listen now. If it's exponential distribution, if we really want to answer a question that has to do with basic statistics, like finding the mean, finding the variance, it means we're actually going to use the mean of the exponential distribution. We're going to use the variance of the exponential distribution. But you know what? The mean of the exponential distribution depends on the parameter. The variance of the exponential distribution depends on its parameter. So which means that parameter needs to be estimated. Now I'm presenting to you now, this is an exponential distribution. If I want to find the mean, if I want to find the variance, I derived that in this class the other time, you know that, right? The mean of exponential, the variance of exponential, but the mean and the variance depends on parameter. You can only determine the mean and variance if you already know the values of a parameter. But how are we going to know the values of a parameter now? We can use the maximum likelihood. Now, this is the exponential distribution where f of x beta equal 1 over beta, exponential raised to power minus x raised to power beta. When you take a look at this now, I want to get the likelihood function. Do you understand how I got that likelihood function? Okay, if I have 1 over beta of that, I think I'm going to show you now so that you'll be able to understand, because I've already jumped some steps. Please focus the board. Okay, focus the board. Okay, so that you can ask me question if you need clarification. Now, f of x, 1 over beta exponential raised to power this exponential. This is an exponential. This is s follow exponential with parameter that. Okay, this is the probability distribution. Now I need a likelihood for this. If I want to get a likelihood, the likelihood of x, given that is going to be the product 1 over beta exponential raised to power that. Now, what is the meaning of this? It means as I'm actually going to have this raised to power n in n term, and this is going to be summation x over that. Who doesn't understand how this becomes the likelihood function of the exponential distribution? Is there anyone who doesn't understand that? Okay, you are good, right? Now I need to get the log of the likelihood now. Okay, the log of the likelihood. So it's going to be n log 1 over that minus summation x over that when I take the log. Okay, now when you take a look at this guy now, so if you take a look at what we have now, so that was how you actually, you know, if I want to rewrite this mathematically, it's going to be, isn't it, beta raised to power minus 1, and that minus 1 can come here because of the log, and because of that, it's going to be minus here minus summation x over beta. Now, when you take a look at this guy now, this is where we normally do the differentiation. You differentiate with respect to beta, you set to 0, and you solve for beta. But you know what? You can even make use of your data here. What is n? Oh, the numbers of data. How many data? 14, 17, they are 10 in number, right? I'm going to plug that in. You see that? I've already plugged that in. Minus 10 log of beta. That was why you see it's going to be minus 10 log of beta. Then summation x. Sum x is going to be the sum of those values. The sum of all those values, I'm going to plug them in. Okay, so that was how you see summation x. So when you take a look at this guy now, in the end, when you solve for your beta, this is what you're going to have. Then you plug in the summation of x, then you're going to divide by 10, you got 16.2. Any question? Is there anyone who need clarification on that? What have we used here? We've used the exponential distribution here. Okay, we got a lot of that. You can walk through this because of my time. It's the same way, okay, that we're going to go. This is another distribution, okay? And this is looking like a Pareto distribution. Let me tell you this. They can give you any form of distribution. They are all functions. It's the same approach. Okay, I want to start an hypothesis testing now, and this is going to be super easy. Any question on the maximum likelihood before I go into hypothesis testing? Any question? Okay, that's going to be the end of the of the method of estimating parameter from a assumed probability distribution using the method of maximum likelihood. Now I want to welcome you into hypothesis testing. We know what we're doing. Hypothesis testing is testing the validity of a claim. Anybody can have a claim. Okay, how do we test that? Okay, because we're always going to have something in our mind. Now take a look at this example. A company can make a claim. You know, let me tell you this. A claim is going to be on parameter. Which parameter we're going to be talking about? It could be mean or proportion. But the one we want to focus on today is going to be proportion. Take a look at this. A DIP company advertises that at least 75% of its customers lose 10 pounds. Do you know that this may be true or not? They've made a claim now. They mentioned 75%. That's a proportion. Does that make sense? Now, and I told you, investigation follow a claim. When you make a claim, how are we know you are right? Then we're going to investigate. Now, a DIP company advertises that at least 75% of its customers lose 10 pounds or more within 2 weeks. They claim within 2 weeks. Don't forget, that could be propaganda. We live in a world where there's a misinformation, disinformation. How do I know the information I'm getting is the right one? And that's why we need to investigate. You suspect the company of falsely advertising the benefit of taking their pills. Suppose you take a sample of 100. When you are investigating, you are not going to, investigate everybody. You're only going to end up taking a sample. You know that, right? Okay. Of 100 product users, and found that only 5% have lost at least 10 pounds, but they claim 75%. Is this enough to prove your claim? What about if 72% had lost at least 10 pounds? What is our goal? Our goal is just to use the sample data to formally test the hypothesis about the value of the unknown population characteristic. What are we testing? We are testing the value of a parameter. We don't know the value of a parameter, but there's a guess. There's a value that is being put forward as a guess, and that's what we are testing. And in testing that, we want to use the sample information. Now, what are the elements of hypothesis testing? In hypothesis testing, we're going to have an assumption, because don't forget, the reliability of our results depends on whether assumptions met. Every statistical model has an assumption, one or more assumptions. Number one assumption here is that you have to use the principle of randomization. The way you're going to take your sample from the population, you have to choose randomly. Choosing randomly means you are giving equal chance to elements in the population. Now, in hypothesis testing, we're actually going to behave as if we're in a court of law. What do they do in a court of law? Oh my God, there are two hypotheses before the court of law. The innocent is not guilty. The alternative, the innocent is guilty. And the court is going to argue about that. And in the end, the court is going to take a position. We're also going to do the same here under the hypothesis testing, where we're going to have HO, the non-hypothesis, and the alternative. I'm going to have HA, the alternative hypothesis. The non-hypothesis is actually a statement about the population that we want to disprove. That's what we call the non-hypothesis. Somebody has made a statement, and we have a doubt about that statement. We now want to disprove the statement. That's what we mean. And of course, the alternative is actually going to go against the norm. And that was why I said this is synonymous with what we do in the court of law. Okay. Now, in the pill example that they claim that at least 75%, okay, we lose of their customer, we lose 10 pounds within some weeks. Let me tell you this. When you are testing hypothesis, your non-hypothesis must have a quality sign all the time. I'm going to say that again. HO, that I call the non-hypothesis, must have a quality sign all the time. But you know what? Alternative, on the other hand, can be less than or greater than or not equal. Does that make sense to you now? Now, let's take a look. Let's reason. They make a claim. Their claim here is at least 75%, right? At least. How can we interpret at least? Oh, right? That's how we can interpret that. 75. What is the opposite of this? It is strictly less than. But if you go to some textbooks will put under the non-hypothesis, some textbook may put greater or equal, but majority they don't do that. What we're going to put in the non-hypothesis is going to be quality sign. Why the alternative now for this, when you know the non-hypothesis, you will be able to know the alternative. The alternative will go against. It's a direct opposite of the norm. Does that make sense? If you don't understand, please ask me a question. Now, this is what I'm trying to show you now is a hypothesis formulation. That is the first step in hypothesis testing, which is also the first step in the court of law. I know in the court of law, they're going to say, okay, are you guilty or not? Before, they're going to call the defendant and they're going to read some stuff. I know the next thing they're going to say, are you guilty or not? Okay, so that means the court will start with the introduction of the case, and of course, that will come in form of the null and the alternative, where the null is going to say an accused person is innocent, because an accused person is innocent until it is proven guilty. So under the null hypothesis is innocent, but alternative is guilty. Does that make sense now? Okay. Now, we now need a test statistic. The test statistic is going to be the formula that we're basically going to use. And the moment we get a test statistic value, okay, what we can actually do is to obtain a p-value associated with the test statistic value. After the test statistic value, we need a p-value associated with that test statistic value. Okay, now when we take a look in the p-value now, we're going to compare the p-value with the level of significance. There's always going to be a level of significance. The level of significance is what we call the level of statistical error. When we are conducting research, we are not 100% perfect. The level of significance is more or less telling the world, this is my level of error out of 100. If I give you 5% level of significance, it means my research can only mislead you 5 out of 100. Does that make sense now? So the level of confidence have to be stated. So what we're going to do is to compare the p-value with the level of significance. And this is the decision rule. When the p-value is less than the level of significance, we will reject HO. When the p-value is greater than the level of significance, we're going to fail to reject HO. Now, let's take a look at this example. Suppose that in your sample of 100 customers, 65% had lost at least 10 pounds in 2 weeks. This will happen. What is the claim of the company? The claim of the company is what is going to be formulated in the hypothesis. Does that make sense? The company claim that at least 75% of their customers has lost 10 pounds. Now, under the hypothesis, this is what I'm going to write. And this time around, the parameter is P, proportion, because they are talking about percentage out of. Does that make sense now? Now, you now investigate. When you investigate 100 customers. Do you know what you find out? You found out 65%. Okay, now the question now is, I need you to be focused and take a look at this. What the claim of the company is the population proportion, 0.75. But the proportion that you obtain from your sample is a sample proportion. In this case, the sample proportion will be 0.65. That is the one you find out after investigating 100 customers. Does that make sense to you now? When you are testing for proportion, you're going to have a population proportion that will come in form of a claim, and there's going to be sample proportion. Now, take a look at this guy now. We now want to believe the sample proportion follow normal distribution with the mean of P0. Do you know that P0? That's an hypothesized value. That is the value you are contesting. Of course, we've done what is the standard error of a proportion. It's going to be P and 1 minus P divided by N the square root, right? Now, when you plug in 0.75, don't forget where is the 100 coming from. That is the sample size. Then it means your P cap follow normal distribution now. with a mean of 0.75 and a standard deviation of 0.04. But don't forget the estimate of that P cap is 0.65. Now, what is the test statistic? Oh my God, I want to go to test statistic now. If I want to test hypothesis about proportion, this is the test statistic formula. It's going to be P cap, the sample estimate, okay, minus the hypothesized value. And, you know, my experience in teaching over the years, I realized that students normally make a mistake. What you're going to put inside the square root will be hypothesized value, not the sample. Does that make sense? You can say P0, right? It means I'm putting a 0.75. What did I get at the end of the day? Negative 2.5. The negative 2.5 is the test statistic. Now, even though, do you know that my T here, anytime you are dealing with a proportion, that very T is Z. What did I say? Z. Now, what I mean, this very T is the same thing as Z when I'm dealing with the proportion. Now, it means I get a Z value of negative 2.5. Now, the next thing that I want to figure out, what is the P value? Okay, if I want to figure out the P value, then I need to put into consideration the nature of the alternative. What was the alternative? Alternative was less than, right? Take a look at the alternative. That was less than, right? Now, if I want to find the P value now, my P value will be P of Z less than that value, P of Z less than negative 2.5. You're just going to go into a normal table. Like in exam, of course, I'm going to give you tables, series of tables. You're going to go into normal table. In the hand, the normal table is giving you that guy is 0.0062. That is my P value. The moment I get my P value, you know what I'm going to do? I'm going to compare that P value with the level of significance. The level of significance that we normally use is 0.05. Okay, when the P value is less than the level of significance, we reject HO. But when it is greater, we fail to reject HO. What happened in this case? Is 0.0062 is less. When it is less, what are we going to do? Oh my God, we are rejecting this guy. We are rejecting HO. When we reject HO, what happened? We are accepting the alternative. Then it means that's a propaganda from the company. The company is not telling the truth. You know, we don't want to live in a world where, you know, some human beings will manipulate us. That's why you are doing statistics. We want to be able to stand on our feet. Okay, anytime you hear any information, you investigate. Okay, and, you know, it's just like somebody come to me and say, "Oh, your wife is doing this," or I'm gonna say, "Okay, thank you so much. I know my wife. My wife can't do that." Or I investigate. So don't always accept whatever anybody tell you. Does that make sense? You need to investigate, because some could spread, you know, a lot of disinformation, misinformation that has ruined people's life. And that's why we need to investigate. That's why we're here. You see that now? That company is not telling the truth. They want to make a lot of sales, you know. Okay, so, and that's why I say the smaller P value, the more the evidence we have against HO. How many more minutes? 5 more minutes, right? Okay. Now then you take your conclusion. Look at the step in hypothesis testing. You specify your hypothesis HOHA. Then from there, you use your test statistic formula. Then you get your p-value associated with that. Then you compare your p-value with the level of significance of the test. Then you conclude. This is my conclusion now. What am I saying? Oh, we assume that HO is true. Let me see. We assume that HO is true and put them burden on proof. Therefore, no. We didn't have. Let me see. Therefore, we can use the p-value to decide on. Let's go back here. I said it's very unlikely we would choose a sample with a few of that. So the evidence, yeah, the HO. So we, just our data provide evidence that HO is false. Let me see. HO, yeah, HO is false because what is true is the HA. We are rejecting HO, right? We are rejecting HO, right? We are accepting that. We're trying to say it is less than. Does that make sense? That's exactly what we mean. Okay. Now, what I've just done now? Do you know hypothesis testing can come in different form? The one I did, the example I did now, is when the alternative is less than. We can have another one where the alternative is greater than, another one where the alternative is not equal. But let me tell you this. It is the same formula all through, but the way we compute the p-value is not the same. When it is less than, the way we compute the p-value, I'm going to show you something. Take a look at this. For hypothesis one, if I want to compute the p-value, is going to be z less. For when the alternative is greater, if I want to compute the p-value, is going to be p greater than. Does that make sense? And p greater than means whatever you check from the table, you subtract from 1. Does that make sense now? What about when the alternative is not equal? When it's not equal, whatever I check from table, I subtract from 1, then I multiply by 2. Does that make sense now? So that's what I want you to see. And this is the decision generally. We always compare p-value with the level of significance. The level of significance is alpha. You see that, right? When p-value is less than alpha, we reject HO. When it's greater or more, we fail to reject. Now, I put more example here for you. This is an example for greater than. You can see, okay? And then we carry out the test. We get the p-value, we take a decision. Okay? It's very, very easy. Okay? Then from there, I'm going to start from here on Friday. I don't want to rush you. This is when we're comparing now. Okay? Two difference of, the difference of proportions. Okay? So we're going to start from here on Friday. But before we start, you can check all of that. They are all easy. Okay? They are easy. Okay, make sure you stay safe and have a lovely day. But for now, everyone, and those who wrote exam online, they should expect their result today. Thank you.